And I got the chat going too.
Yeah, thank you. And I share it again.
Okay.
Okay. And here we're gonna go to the what to call it, the lab tree. We describe it all, everything related to the measurements of the moon orbit, either Ganymede or Titan, Oberon or Triton. And then we went to the procedure B, this section, and see how the graphs is showing. And also same thing on the mass and distribution, how to calculate the mass and the value of the mass of the Jupiter based on that observation. And I'm just going to show you, this is a Excel file that I created for the Ganymede that I observed. And based on this observation, I added everything in one Excel. The reason is that normally, if you do that, you can easily copy and paste on the Astromancer and get the graph and the other parameters that is related to the this graph for the period and getting the period and amplitude that is identifying the semi-major axis of the planet. And therefore, this is handy. I put it this one, but if, as I mentioned last week, if you are interested, we can put it either how many, doesn't matter how many, but if you guys are okay, we can do it kind of, if we do the Jupiter or Uranus or Saturn, we can collect all the data and compare it, what the result we can come up and create a kind of a semi-scientific article based on these measurements and comparison on the data that we provided versus the actual value that is provided. And I can share it with you, this Excel file later on. And just think about that, and if you want to continue on that one. And then going back to the lab tree, after this set of the data that is related to the gas giant, we go back to the Venus phase. The Venus is actually on the background information, provided very good and handy tools here that we described it before on previous weeks, that if the we had the heliocentric geocentric vision and heliocentric, how that kind of curves that we get it based on the angular diameter of the Venus versus the phase, it's gonna be different. Here we're gonna show on the phase 3 what actually we can do on this measurement. Here for the Venus, for the other gas giant that I mentioned, you did a measurement like this on Astromancer. You have taking picture 14 days back to back, but on the Venus, because this Venus is very difficult to take a measurement, we're gonna use the whatever data sample are already on the SkyNet that I'm gonna show you. Here on the measurement, we have to take two measurements on the picture. Normally, if you look through by bino or a small telescope, when it is Venus like a phase, it's gonna see the crescent of the phase very easily. And I see it on my 6-inch and 4-inch telescope, and also with bino, both of them easily you can recognize the crescent of the Venus when it at that case. On here, we're gonna measure two parameters. One is they call it illuminated angular phase, and another one angular diameter. Angular diameter is from tip to tip, and the illuminated angular distance is from the across the crescent or size of the crescent that you had, as shown on this picture. And we're gonna see on Afterglow how we can do that. And the phase, based on the definition, gonna be like this. You divided the smaller value to the larger value, it's gonna be the phase. phase gonna be 0.1 to a little bit more value, 0.2, 0.34. We're gonna see how much the value is gonna be different. And then based on that, you bring the data on the Astromancer. And as you know, if our solar system is geocentric, the orbit of the Venus and data that we're gathering gonna be distributed on this area that is highlighted by blue. But if it is not geocentric and heliocentric, you're gonna see the data is distributed along this line, around, not exactly, but around this edge. And this is one of the very easiest way that you can prove it. The heliocentric is correct, and by simple tools that we have right now, we can prove that ancient astronomer from Greeks to before Copernican that believed that there is a geocentric is not correct, only by measuring the Venus. This actually experiment that is done like this is done by the Galileo in 1609. Therefore, whatever you do here, you just putting your feet on the shoes of the Galileo and measuring the things that we have. Any questions so far?
Yeah, sounds great.
Okay.
Great.
And then let me go to the in here on this consideration. We go to the Afterglow. And Afterglow, I downloaded this Venus pictures, and I'm going to show you when it is going to be downloaded. You go to the open files. Do you see my Afterglow?
Yes.
Okay.
Yeah.
Okay, when you go to Afterglow, you open the file, and you go to the, if you go to your pictures, you go here and user, but we don't want to go here. We want to go samples, and you go to Astro 101 lab. And Astro 101 lab, Galileo on Revolution, lab 3, and Venus. When you click the Venus, there is a 7 picture taking at the time that the Venus has a measurement. I already click all of them. You click all of them and open, and you're going to see it on the left side. You can do it right now if you want to follow up with the procedure that we're going to describe on the screen. Then you come for each of them. First one, you click on the first one, you see the Venus is here, and make it on the center, zoom it.
Okay, right now we don't have anything that we can see on your screen. It's just white.
You don't see it?
No,
Oh,
it's got
something
surprised.
is, yeah, something is happening. Let me do it again.
Okay.
It is some special things comes.
It had your list and just white in the middle. It was still
Yeah,
loading up, looks like.
okay, let me do it again. Something.
There we go. Yeah, I just uploaded Venus myself. That was actually pretty quick.
Professor Abbas, if we weren't able to take a picture of Venus during lab 1, what should we do? Because it doesn't look like it's currently observable.
If you take it on the first, do you see the picture right now?
Yes.
That's good.
Okay, yeah. If you're able to take it on the lab 1, because here normally you have to take several pictures during the different times. If you can able to take a picture of the Venus either on the lab 1 or either later on by end of the semester, you can do the same thing based on your own data. There is no things, but the problem, you have to make sure you take a picture from different phases. For example, when it is, let me go, normally when you open this one, you just click on the bright object. As you see it here, the crescent is a little bit large and kind of not this. If you go click on the 7 gonna be, you see, a little bit more crescent-like. As you see at the 7, if you can make it several measurement like this one, this one that is a little bit more fatty crescent or more narrower crescent, if you have all of them, you can make it 6 or 7. You can do the same exercise with your own data. That's answering your question. Is that the one that you're asking for?
Yes.
Okay, that's good. Therefore, here, normally what you should do, you have to take a click on the bright object, because if you don't do that, it's gonna be like this picture, and this is not good for the taking the measurement. You make it a bright object, and you enlarge it as much as you can, be able to see the edges, and then you go here on the setting and make a synchronized setting. It means that when you synchronize the setting, it's gonna be consider on the all of the object, all of the pictures together. For example, right now you're seeing the Venus one. If you go to the Venus 7 and Venus 4, also you're gonna see the same thing. And therefore, that's a kind of measurement that you needed. You can do it with this kind of item clarification to make sure that you don't repeat the things again and click many times as needed. Therefore, this is one of the cool tools that you can do that on the observation. Then what you need to do, go to the latter tool, make sure here is centroid click is off, because we don't want to, when we click, because if it is on, when you click any place, it's going to take it to the center. We don't want to go to the center. We're going to measure the edges. First one on the shorter distance, we go from here to somewhere here. This is a kind of judgment. It might be exists here, as you see it here. And then you look through lower right. Let me see if I can top it here. Yeah, come here, and you see how much it is, 10.24 arcsecond, length of this line. Then you come to the Excel file. You see my Excel?
Yeah, we see it.
Yeah, looks good.
Therefore, you click here and paste it. Oh, sorry, I have to. You click here and identify 10 point something 24 to that you had it here for the first image. Then you come back to the here, go from tip to tip. From here to here, it's gonna be 14.7. Then you go back to the here, 14.7. Let's see, 14.7 or 7.2, yeah. 7.0. 2. You don't need it to be more meticulous. Just one decimal point after one number after the decimal point is good enough. And you do for this one, and then phase is going to be the shorter value, illuminated angular distance, divided by angular diameter. And that gives you the value of the phase. Here you see it about 67%. And I can repeat it the same thing for the others. They do the same. Let me do one more time for one of the others. Let me go to the number 4. And here I zoom it in.
So as Boss is zooming in on this, one thing I tend to do is I'll scan an extra distance across it. And then the graph, you'll see the bump, and you can go along the graph itself, and it'll give you the edge on each side, a number. And you can subtract those to also get the span of the object.
Yeah, that's a good point. Thank you for helping on this. Therefore, here you do the same thing. You just come measure on the cross. It's going to be 10.0. You go back to your item. This is number 4, 10.0. And then angular diameter, tip to tip. It's going to be 29.9. 29.9. Okay. Then all the phase and all the information is needed. The only things that you needed to take it to Astromancer is these ones. Only we needed angular diameter and phase, because we want to see how phase and angular diameter are going to be changed with each other. We go back here on the and Astromancer. On the Astromancer, let me go to the beginning to show you. Here, you just click on the Astromancer, and you come here and choose the Venus here. There is a many different option on OPIS or place in the space. We click on the OPIS, And this one, the data is created, this previous data, whatever you have deleted. Let me delete again. Okay. Then come back to the here and copy and paste. Copy and paste. Control V. It's gonna be see here. As you see it, these blue dots are the measurement that we did it on our 7 pictures. 1, 2, 3, 4, 5, 6, 7. And this is very clearly show that it is out of this graph that is representing the geocentric data. And therefore, here we can prove it easily by this 7 picture. Our solar system is heliocentric, and Venus phases that gonna be observing, it's gonna show exactly what is happening. And that is reason that is highlighted on background information of the lab tree that is highlighted here. If this is the one that you see at Venus, if we look through it based on the geocentric observation, and this is the way that we can see it, the phases of the Venus on the heliocentric. Remember, in this time when the problem is that when the Venus is full on the other side of the sun, normally we cannot observe it because this is the Venus is very small and sun is big compared to the size. Either it's gonna be somewhere around the disk of the sun. Therefore, this one, this item, when we have a Venus full, or this one and this one, is very difficult to take a picture or observe. Whatever we have taking the picture, gonna be in this region, around this region. Therefore, as we see it, we have 7 picture. Is actually what we needed: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We cannot take a 12 picture on different phases of the Venus because of this 3 portion are very close to the sun, and therefore it's gonna illuminate it on the glow of the sun. The only you can take a picture instead of the 12, you may take it easily 7 or 5 or 6. That is we showing on the sample data on 7 picture. And this one is actually show that this line that is heliocentric and this is geocentric, or data show that or heliocentric is correct. As you see it, the numbers that is showing on this graph 1 and 5 related to the different position that you see it on the picture when you're taking this graph based on the description that is on the WebAssign provided. Any question? I hope I didn't go very
really
fast and you catch it what item is needed. And then you apply this, you can provide based on the data on the sample data, and you fill it out this information on the table, and then save the graph. When you go here, you can save the graph, enter the data, make sure you put the titles. This is angular diameter arc second, this is phase, and the title gonna be phase versus size of the Venus, and then save the graph and put it on the choose the file for the WebAssign assignment and answer the question. This is very trivial question based on the brainstorming that you did. Are your measurement more consistent with geocentric or heliocentric model of the universe, and why? You describe whatever you think in your mind based on this activity that you've done, and also discuss the significant source of the error. That what source of the error exists, either you didn't see all the lines, all the points on this sign line, or what other sources that you may consider. And therefore, it's kind of things like sometimes, because most of the time Venus is very close to the horizon, that atmospheric blurring may happen, or it may be shade glow created on the, remember in here when we measure it, let me see where we are. Yeah, when we measure it, we just go from here to here, but is it actually edge to edge or tip to tip, or here cross to cross? And because of that, we may have some errors on this way that you can describe it on your assignment on the lesson. Okay, hopefully this conclude what we had in here. I stop by ask a question if you had any.
No,
No?
it's really good. I'm going to share
Okay.
real quick if I can.
Go ahead.
My screen real quick and just kind of an alternate way to kind of look at it. You know, we get into this, there's still some discrepancy you're going to get into. You really can't avoid it. But yeah, and you really have a couple options like going edge to edge. Now, I always click this thing too many times, but if you can find the one edge and you're scanning across, this is going to give you a pretty good value for the width of this. You can see that. But just kind of mentioning another approach would be going from one side to the other. And one thing I discovered is the farther out you go, the easier it is to define where that edge is really at, because it really kind of bunches it up. And you move your cursor along here, it will actually give you readings. So you can take two readings, one from each side, and get a value for that. Now, we do get this discrepancy. There's a bit of a range on where you're going to pick that spot, and that happens both ways, I believe. But I think if we're consistent with this one to doing the scan down from the top side across, um, that consistency should null out the errors. The percentage is pretty good. That the ratio is going to be pretty accurate. I think both techniques will give you good values. I didn't do this because I'm a little lazy sometimes, and I can get those spots pretty quick both ways. So just want to
Yeah,
kind of share that. There's a
no,
couple
no, no.
options.
It was very good. Thank you for this is one of the good way, second way that you show it. But the problem is that it is not automatically calculated, but you have
Mhm.
to measure it one by one and subtract it, and then. But is actually another method. You can compare it to see which one is more accurate, and that's kind of very good scientific way that you can highlight in your last question, that source of the error, and compare these two techniques together. That's gonna be a good value as well. Okay, let me go to the second one, second item that we have. Just 1 second. On this lab 7, let me make sure that, yeah, screen is shared. Here. Okay, here we're gonna go some background information about the what the lab 4 is gonna consider. Lab 4 and lab 5 and 6 is a starting point to cosmic distance ladder measurement. On the lab 1, 2, and 3, we just focus on the lab 1 as general, taking the picture from SkyNet. Lab 2, we went to the measuring the dimensions based on the Earth, on the Earth itself. And item 3, lab 3, we went to measure the distances on the planet, on the solar system. Here, we're going to go a little bit further, and we learn a topic, we call it parallax here. And I sent it some graphical representation and attached in the email. You can open it and read it. And if you had any question, let us know. But this is kind of very basic things that if we learn this one, gonna ease us for the remaining part of the class on this session. For the first one, we're going to use the parallax. What is the parallax measurement distance on the object on the Earth? And then we're going to go based on the Earth diameter, and then we go to the within the solar system, and then we can go to the nearest star. Therefore, we're going to use the parallax. We're starting from Earth to within a Earth diameter on the solar system. And also, we're going to use the other solar system object based on the AU and the astronomical unit. And then we're going to measure it, how it's going to be worked. And equipment you needed is only projector and kind of good measurement tools that we have. As you see it on the curriculum that we had for the distance and other measurement, we are here on the lab 2 and 3. And on the lab 3, we went a little bit offside of the distance ladder. We just go measure of the some orbital diameter and Kepler laws on the planet. But on lab 4, we come back to the parallax, and we're going to use the Earth base to measure the data. This picture is very good. As you see it here, one question, as probably you know, but I want to emphasize this one. As you see it, many of the stars on the sky, in the old days, people they thinking all of the stars are like illuminated um, nails or kind of bright object that is attached to the celestial sphere. And it shows they just, in the old days, astronomers think of like that. And they think that celestial sphere concept created in a way that they thought that all the stars are at the same distance and they attach to the celestial sphere. And we see that they are moving around ourselves. That's the kind of concept of the geocentric idea of the universe created. But if actually we look through the object, we can differentiate which one is the planet and which one is a star. Planet, they call it planet because planet in the Greek and Latin means that it moving. It's not like, for example, as you see it, a star on the constellation Orion or Cygnus or other constellation, always they keep the same distance and same pattern. But the planets is moving around. Sometimes it's here, sometimes it's here, sometimes go back and reverse direction and go the other way. And how we can differentiate if we look through the sky, how we can differentiate, for example, Saturn, we see it last night with the other stars. Do we have any rough and approximate and very quick idea to differentiate a planet that we see it versus the other star in one night? I know if we look through it for many many lights or many days, it's gonna change. But if at a certain time of if we don't have any knowledge, we're gonna look through it the sky. How we can differentiate if this is a planet or this is a star, and which one is planet and star at the one moment of the time on the night?
See how fast it's moving?
No, the question is that we see it right now, but at the moment you don't see it any movement. If you look through several nights or several days or several months, you will see it, the location is moving. But if we look at one moment, at the same moment, you don't see it any movement on the night.
Maybe like color. Like I know like Mars appears like orangish. So.
Yeah. One of the key things is that they have very distinct color that has Mars is orange or reddish, kind of Jupiter is blue, white, and the Saturn is a little bit reddish, a yellow color. But another thing is that those are also bright. Venus, for example, is very bright, or Jupiter is bright, but Saturn and Uranus and Mars is not bright, is not like other stars. The other main differentiate is that the planets are twinkle. It means that if you look through it, it doesn't twinkle. The stars is always just is like just twinkling, and the light comes and goes, and just it's like a sparkle in our eyes. But the planets steady, they have steady lights. The reason is that the stars, although they have very powerful lights, but because they are very far away from us, the light that is reaching us is very narrow because of the distance that you see it, because of the parallax. We're going to see it later on. But the planets are very close to us. Therefore, it's actually, although we see it in light, but if you just zoom it in, you will see it a little bit more than a circle. It is kind of an area, you see it. It's not just point of the light. Because of that, if normally the light is coming, has to pass through the atmosphere. And when pass through atmosphere, there is a mini aberration or kind of fluctuation on the atmosphere, on the temperature. Many things, wind and other things may prevent the light reach us at the end. Therefore, because of that, because of the light of the stars is very pointy and very narrow, it sometimes you see it, it's like a sparkle and twinkle in our eyes. But the planets, because they are not point of the light, there is a sphere, a little bit of sphere exists, and for example, moon is about half a degree, but the planets is not that big, but it's going to be few seconds or few minutes, few not few minutes, few second sizes. And because of that, we're reaching the light from many points on that disk of the planet. Therefore, because of that, we see it, although we have aberration and fluctuation on atmosphere, with at least one of this point of the light and photon gonna reach our eyes. Because of that, we see it very steady. On here, the first one that we're gonna go on lab for, or parallax observation, gonna be based on the baseline. And another thing is here, if you look through these two stars, A and B in this picture, it seems to be both of them same brightness. It looks like, for example, this one is very fainter, this is fainter, but this one is bright, this one is bright, this one is bright. But A and B, it seems to be both of them that is showing here. It seems to be almost the same identical that you had here. But how you can differentiate these two, either they are on the same location or no. This is one of the key things that we learned, that if we have know the parallax, we can identify if they are the same, and the parallax identify this one is larger distance from us than this one. It shows that this one brings us more light, therefore might be much brighter than A. That we're gonna learn on here how we can do that. To get a concept of the eye, this is very good picture that here you can do that in your room that you had. You look through the, for example, you put your finger on front of your face and just look over the whatever you see on the front of the, on the other side of the room. You may have several items like a book, letter, pen holder, or light, or a cup of the coffee. And then if you look through it, as you see it, your baseline for the parallax is your distance between your eyes. And if you look through, close one of the eyes and open with your other eyes, you see it, this one on different location. And this is very simple way that you can consider parallax. On this parallax, you're gonna have your finger or your hand gonna be point of the parallax on here. And then you have two triangles, one based on your face and one based on the far distance object. Therefore, if you want to consider this distance between them and distance between you and the object, you can easily use simple geometric consideration, like the one that is shown here. For example, if we look through from this side of the Earth to the sky, we may see it, for example, this object on the space, it is located on A prime location. And if you look through from point B, it looks like this one compared to the far distance object. This other object that you see it is far distance. This is shorter distance for us. This is one of the nearest star that we have. Therefore, you see it in here. Therefore, we can measure it distance and here how many arc second we have. And then if we know this diameter of the Earth, we can easily measure the value. This one shows on the picture how it looks like. Here, as seeing from point A, here as seeing from point B. And we can measure this distance to calculate the parallax. And same thing on the in here, or one of the key things on the parallax is a measurement distance between the two base of the parallax. Here, when you have your eyes, base of the parallax is going to be distance between your eyes. Here, base of the parallax is going to be two sides of the Earth. It means that diameter of the Earth. And here, the parallax is going to be distance between the Earth around the sun on two locations 6 months apart. And therefore it's going to be, if the average distance between the sun and the Earth is 1 AU, we call it AU, or therefore it's going to be 2 AU. Therefore, if we see the object going to move from this location to this location, we can measure this angle, angular split, that is based on the parallax consideration. And this is kind of item that is showing here. We have baseline if we consider Earth-based parallax, this baseline and this is angle of the shift on the location of the object we are observing. And we can easily calculate based on this simple proportion. Theta compared to the 360 entire circle is going to be equal to the baseline and the circumferences of the big circle of the consideration on this geometry. Same thing, you can do it on the stellar parallax when the baseline is going to be 2 AU, as you see it on this example, this one. Therefore, here, we're going to have the same proportion. Theta, whatever angular shift that you see at the location of the object in the sky, like this one or this one, you can measure it like this. Theta divided by 360 is equal to baseline and divided by circumstances of the big circle. The question is that, okay, theta, I can measure it. Baseline, I may know, measure it with different way that we learned before. But the question is that we have how many parameters? 360 is the constant, baseline and theta we have. And we don't know this circumstances. And how we can calculate it. Then we write the proportion like this, baseline divided by circumference and theta divided 360. And here, this is the kind of things that comes in the consideration. If you consider this object, you just put it from this object to the center of our observation. This is going to be distance. Therefore, instead of what is perimeter of the circle is, 2 pi times the 2 pi times the radius. And radius is actually here the distance of the object from us. Although here it is the sun, and here is more closer. Here is center of the Earth. But actually, doesn't matter because the size, the distance is very big. Although we're measuring from the center of the Earth or center of the sun, but actually this gives us very good indication what the object distance is. Therefore, we come here and replace the perimeter of the circle with the 2 pi distance and solve the equation. And distance is equal baseline divided by 2 pi, 360 divided by theta. And this is a simple way that we can calculate the distance based on the parallax on any of this way. And you can do that same thing on this observation. Here, your baseline is your distance between your eyes. You can measure with a ruler and easily identify. And you can do it a very good example in your room to see, or in your backyard also. You can do the same thing and measure how much the distance you have by simply measuring the angle. For the angle for the backyard or in your room, you can use the simple geometrical devices that you may have in the geometry, and you can measure it accordingly. Any question?
No, this is really good. You guys doing okay? It's so a personal story on this. My wife and I were in an accident many years ago, and Lisa had a patch over one eye, so we had one eye. And one thing you find out with one-eyed people, one-eyed animals, is you lose that depth perception because of this idea of parallax. And so earlier, I remember somebody had a friend who had a one-eyed cat. And what this thing would do is constantly run into things because it couldn't gauge distances, didn't know how far things were away. But it was scary with Lisa driving initially because she was driving, but she couldn't tell how far things were away from her. And you don't think about when you drive, you need to know that so you don't rear in the car in front of you and stuff like that. But the easy solution was use parallax. I just told her, take your head, just move it side to side. And your brain will do this. That's why our two eyes, our stereo eyes, are so powerful, because it uses parallax and your brain is configuring it out. But it is a question about how far out is this good for. At some point, parallax does break down. And if I guess you have a little trouble, just shake your head a little more and hope you don't get a ticket for driving down the road like that. But parallax, good technique.
Very good, very good. Yeah, and there is also, as I mentioned, you can do this activity by simple things in your room. You can just point it with your one eyes and other eyes to see if you can measure it, the kind of information like this as you need it, and then also in your backyard, also you can do that. There is one exercise I'm going to show you here. This is actually exercises showing in this example. This is actually for the individual that is on the Chapel Hill University. Therefore, this shows that, for example, several, probably at that time, there was a crane for the construction. I don't think they have anymore. But you know, this you use a protector to measure the distance, and it gives you a very good way how you can use these simple tools to make a measurement of the angular diameter for the object, either in your room. You can do that, repeat this one for your object in your room, that you can verify by actual meter measuring tape as well, or laser tape as well, or you do it on the backyard. You check how much this parallax techniques is close to the reality than the actual value that you have. Therefore, this one is not kind of applicable for you, this exercise, but you can repeat it with a simple same way with different object, that instead of taking this actual picture that is related to the campus and the Chapel Hill. And next one, we're gonna have some exercise related to the distance of the asteroid measurements in here. And this is one of the key things that all the procedure that we have, procedure B here, B1, B2, one of them is main belt asteroid, and second one is the identified asteroids. For example, in here, you can look through the tutorial that gives you indication how to do that. But simply, one thing that you can do is that I will show you one of them. For example, with repeating the tutorial that Professor Dan does. But you know, this picture that you had here, this one is taken by the SkyNet or provided by you by the sample data. And then this one, another one that we call it upload the final DSS image. And DSS image is here. If you look through, for example, in here, this is one of the sample file that I created. Before doing that, let me close this one. You have this data, observe it, but you don't know which one is asteroid, which one is not. And then you have to click this tools setting here. You have another option in here. They call it import DSS. DSS stands for digital space, I think, technology, or sky system. I forgot the designation, but when you click on that, it's gonna upload the same area that is picture taken, this picture. If you are on this picture and click on this, it's gonna bring the same area that you had on this picture, but it slightly might be different on this case because that's gonna be different. For example, if you look through here, you can check the coordinates to see how it looks like. Another technique on the Afterglow is that when you click here, you want to compare it. Right click here and make it split down. When you split down your original picture on up and the actual picture digital survey of the sky is down. Therefore, you can compare it. Just make sure that you just make it like that. But here, you have to see if this is a correct one. This is coordinate 143.11, 7,473, and this one is different. I don't know, this one might be some other item. This one doesn't look like similar to each other, but anyway, this is the one that I check it with based on the available sample data on the Afterglow, but I recommend you go to whatever description that Dr. Dan provided. Let me go over on here on the Astromancer. It's going to be short video. We go and look through it.
All right. In this video, I'm going to overview a skill that you learned back in Lab 1, and that is how to identify an object that's moving through your image. Now we do this by comparing your image, or the image your class acquired, to an archival image acquired a very long time ago as part of a grand survey of the entire sky, now called the Digitized Sky Survey. If the object is moving across the sky and it's in your field of view now, it almost certainly wasn't in the same field of view, in the same place in the sky, back when the archival image was taken. So by comparing the two, you can identify the moving object in your image. Now, back in Lab 1, we did this to identify a dwarf planet. In this lab, we're going to do this to identify an asteroid. So let me share my screen. Okay, here we are in Afterglow, and the first thing we need to do is find your data. As described in the previous video, this is a special observation. It's not just an observation of an asteroid, but it's two simultaneously acquired observations of this asteroid. One using a telescope in the southern hemisphere, and one using a telescope in the northern hemisphere. To achieve this simultaneity requires a higher priority special access level called Target of Opportunity, or TOO. And this isn't something that we can just give to everyone, but we did give it to your instructor, who then acquired these observations on behalf of the entire class. Now, to find these observations, you go to Open Files, double-click on SkyNet, and in here, you'll find two directories, User Observations and Group Observations. The observations that you have acquired throughout this course are in the User Observations directory, but your instructor's observations, along with a great many other observations, are in the Group Observations directory. Since there will be so many observations in here, your instructor will let you know which folders correspond to the observations of this asteroid. And for the purposes of this exercise, identifying the asteroid, you only need to open one image from either of these observation folders. Now, if your instructor did not acquire fresh data, you're welcome to use archival data of an asteroid acquired by the SkyNet team some time ago. To find this, you go to Files, you go to the sample directory, Astro 101 Lab, Lab 4 Parallax, and here you can see a handful of asteroids acquired in different semesters. Any one will do. I'll go into the most recent one, and you'll see two folders, Parallax and Movie. Go into the Parallax folder, and here you have two simultaneously acquired observations from different telescopes in different hemispheres. Again, to identify the asteroid, we only need to open one of these, and I've already opened the first one. We see it here. So we have a field of stars, and somewhere in this field is the asteroid. One of these points of light is the asteroid. And to figure out which one, we're going to open the Digitized Sky Survey, the DSS. So we come over here to the gear icon and import the DSS. It may take a second, and it will load as a separate tab in the same image window. We'll now want to split the screen. So you can right-click on this and split down. Down here we have the DSS. Up here we have the class's image of the same field. And looking at the two of them I can already see the pattern. I can match up stars across the two images. Now, to help with that, we go back to the gear symbol and sync the orientations, and it should be set to sky. And when you do this, the two become locked. You can zoom into any part of the image and find stars in common. And we'll want to mark those stars that are common between the two images, and that will help us find the one point of light that is only in our image and not in the archival image. And that is, of course, the asteroid. So let's go to the marker tool. I'll turn centroid clicks on. So let's start with this pattern here. 3 of them in a row of intermediate brightness. Corresponds to those 3 right there. We have these 2, this one and this one. This really bright one is this one. We have kind of a double here and another little one. There's the double, the little one. So by now, it should be pretty clear that this is the asteroid. You don't have an object of comparable brightness at this location in the DSS. So let's click on it again and label it. Now, of course, this is the asteroid. In this image, you will have your own image of a different part of the sky, of a different asteroid, and you'll need to find the asteroid in your image. But once you've gone through this procedure, all that remains is to save JPEGs of each of these using the camera icon here and here, and then upload those JPEGs into your WebAssign lab. Okay, that's it.
Professor, for this sort of like cross analysis, do you have any suggestions for like solid points of reference? Because like I was with him for the big star one, that's pretty easy to grasp. But like all the other like little ones lying around, that seemed like witchcraft.
Yeah, is actually that's correct. In here, in this example, I can see it from beginning that bright star was an asteroid. But I think the professor then provided this one to give all the steps that needed to make sure that if this is not the case, if sometimes the asteroid very close to the same brightness of the stars to see it. That's the reason that they provided. But also, as you see it on the beginning, he described something that some of the instructor may do a special TOO, but that is for a long time ago. I think in the last 5 or 6 years, as I remember, nobody able to do that kind of TOO test because of the many different reasons. And for example, neither I or John, we can do that kind of things and ask you for fresh things. Therefore, we have to use whatever sample that we have in our data. Okay, any question? I think at this moment, we just on top of the hours, we just discontinue. Here, so far, we learned how to use the parallax and what the parallax is. And also, feel free to read the 2 attachments that I sent in an email for you, one for the celestial sphere and one for the parallax, and do some sample example on your room, your backyard, to get the measurements, and also find the asteroid in the sample data if you can. That's therefore on this lab we don't have any observation. We're gonna use whatever data is collected before, and I think next week also we're gonna have the same thing. We're gonna review the end of the lab 4, very short, like the one that we did it on lab 3, and hopefully we're gonna go lab 5. Lab 5 gonna be very extensive and important activity that we're gonna do some observation on, and also lab 6. Lab 5 and lab 6 on the OPIS2 gonna be key values for actual astronomical measurement of the deep sky and nearby object on the sky. Any question? John, anything you want to add?
That's really good. I'll tell you one thing that I did last night that made me think of this a lot too, with parallax was um, I took had two green lasers. I was checking the batteries on them, and then being like a kid, I put them side by side and I was beaming them around the room. So I had two dots that were tracing each other. I thought, lo and behold, I have a perfect demonstration for parallax because as you go farther away, those dots were separating. You come in, they come in close together. So I was out in the hallway, and I'm gonna use this for a lab demo. You take the two lasers, and you can actually show how the parallax goes, how things naturally get wider at distance, even though they look parallel. That slight angle is enough to do it.
It's very
I
good
was,
example. Yeah, they're very good example. I didn't thought about that.
yeah, it's just being a kid, you know.
Yeah,
Getting back
that's
to
good.
Next week we have sessions. Now the week after that is Thanksgiving week, so I wasn't sure how we were going to run that. Any thoughts on that
Let
Tuesday,
me
Thursday?
see.
What do we
Let
have
me
planned?
see. Let me see. Next week we're gonna have 20, and the other week gonna be 25 and 27. I think 25 and 27 we're gonna make a holiday or close the session, if you agree. Therefore, we're gonna
Okay.
have 13. Next one is 18 and 20. And if all of you agree, we can cancel the 25 and 27.
That
Yeah,
sounds
Okay.
that
good.
works for me.
Yeah.
And we have a lot of
Therefore,
data coming in for our past observations for
yeah,
Jupiter and
yeah.
all that too.
And
So
also next week, 25, 20, we're gonna do some uh, extensive observation on the lab 5, hopefully, and on the 18th Tuesday, we're gonna go on the 1B for the mineralogy of the moon, and a little bit more further on the MW. And hope you have a good time. And just ask a question if you had anything on the email or on the sessions.
yep, just reach out.
Okay.
Yep, good,
Thank
good
you,
to see you guys.
everyone. Have a good evening, and see you next Tuesday or next Thursday. Have a good one.
You
Thanks.
too.
You have a great day.